Okay, I think it should be recording now. So today, I wanted to go over an external flow simulation. So just a review of last time. We went over an internal flow simulation on just like a pretty simple geometry. Yeah, and there wasn't much anything that was really complex about it. So things went along pretty fast, and we didn't really do much in the CAD. But that changes when you're working with like a full car geometry or whatnot. If you're working with like a larger assembly, maybe like maybe the entire front wing package or an entire rear wing package, there could be other adjustments that you do that you could take advantage of in STAR's own like CAD software suite, whatever. So yeah, I will get into that a little bit today as well. So right off the bat, I just want you guys to notice something about this this CAD model. It is not as accurate, and it's missing a lot of intricate geometries that our actual full car CAD model has. Actually, why don't I just pull up the full car CAD so we can see it side by side. Okay, so anyways, I guess the CAD model was just being weird, but I mean, I can just point out a couple of things here. Like there's none of the powertrain stuff in the car. We can see that mounting is missing here. The suspension geometry is simplified. There's a simplified dude in there. And just overall, there's just a bunch of CAD simplifications. The overall body of the car, you can see, is pretty simplified from before. And the reason for this is all of those minor, like smaller geometries aren't going to make a large difference in terms of the values that we're trying to calculate with CFD. So it just makes it easier to basically remove some of those complexities and make a simplified version so that it's just easier on the compute power. Yeah. So basically, when you have your simplified geometry, you want to do the same step as before to export it. So that's just file and export, and I'll send you the parasolid once we export it. And then you can just like Control A or something to select everything that you want. Or if you want to like select specific parts, then you would correspondingly like select the parts that you want to export. So let's just say that we're going to export the entire CFD geometry. Just click OK, and then you can name it whatever you want. Yeah, so I already have a parasolid file, and I will send that in the arrow chat so you guys can follow along past this point. So just bear with me for a second. Okay, it should have sent in the arrow channel. So yeah, so just download that, and we can. Oh, also here, wait. Also download this. Oh, wait. That was. Okay. Yeah, download the duct width baffle thing also. I don't know why it like shows the text inside of the file. Whatever. So anyways, so basically I wanted to show you guys how to basically replace like a part in STAR itself, which makes things a little bit easier. So basically what we're gonna do is we're gonna import this car, and then we're going to replace the duct with this duct, which has like this sort of flat plate in the middle, hopefully, which can help with flow separation and I guess we'll find out if it really does or not by the end of the simulation. I haven't tested it yet, so I don't actually know. Okay. Now let me reshare my screen. Okay. So let's create a new a new file. And then just make sure that you select like your default parameters that you usually do, and then just click OK. And then this should pop up here. There shouldn't be anything under 3D CAD models since we'll be adding it. Yeah, you should see everything that I see here, and just like a blank screen over here. So what we have to do is import our 3D CAD model. So that'll be your .x_t file that I sent in the chat. So the way to do that, right-click the 3D CAD models, then click New. Now it opens this this CAD window over here. And then from there, we can import our part that we want to study. So let's import our CAD model by right-clicking the 3D CAD model 1, then going to import, then to CAD model, and then find your .x_t file, and it should be, yeah, this one right here, full car CFD GM_ flat front wing and no rear wing. And then everything here is good. Click open. So now we have our CFD CAD set up. And also just to note, the reason we don't have the rear wing on here is because it would just be extra computational power. That's not necessary, since what we're trying to see or study in the simulation is effects to the radiator mass flow. So that would not be necessary. Okay. So does everyone see what I see right now? All right, cool. So now what we can do is replace that duct. And the reason why we'd want to replace the geometry inside of the star file is, I'll give you an example right here. Like basically this sim file over here already has everything set up as we want it. So it becomes really simple to just go into the 3D CAD model and replace the geometry inside here, and then just erase the solution that was created by the simulation, and then remesh the simulation, and then just run, so that you don't have to like go through this entire setup that we're about to right now. So yeah, that's like the reasoning behind that. So the way that we want to basically replace this part, STAR makes it actually pretty easy, surprisingly. Basically, all you have to do is right-click the import CAD1, and then go to model re-import down here, and then you can click that duct with baffle that you should have downloaded from the arrow channel, and then click open. And then you can see the previous CAD model on the left, and then you can see the parts which have been attempted to match up between the top and bottom. So basically, what STAR does is it shows all the parts that aren't matching currently, and you can see that the duct is missing, meaning that the ducts were already matched together, so that we don't really have to do anything here. All we have to do is add all the like CAD bodies that were there before to our like new model essentially. So the way to do that is like click the top, you can scroll to the bottom, shift click the bottom one, and that just basically highlights all of these. And then you can just click add, so that'll basically add all of the non-matching parts from the previous model to the new model. And yeah, just click add. And now we can see like under modified bodies, we have the old duct on the top and the new duct here on the bottom. Yeah, and usually what will happen if you change the geometry a lot, let's say you change the spline of this geometry to be like have a less diverging angle or something like that, you would have to most likely match the faces as well. So the way that you do that, so there'll just be like a pop-up which comes, and then you just basically click the corresponding faces on the top and the bottom that match. And then STAR will basically just replace the body. And then what we do from there is just click OK. And here is our CAD model. Where's the duct? It's down on the bottom. So it looks like STAR didn't like perfectly figure out where to put the duct, but that's okay. We can just move it now in the CAD geometry. So the way that we would do that is you can go to or open up the node next to body groups, open up this body group 1, find the duct, and then what we want to do here is essentially transform the location, specifically translate the location so that it's the outlet of the duct matches up with the inlet of the radiator. So the way that we do that is right click duct and then go down to transform and then down to translate. Now it brings up like this little menu thing right here. And you can basically just drag on the arrows to move around to like the location that we want about, and then we can precisely change the numbers to better to get a better like fit on the radiator. Also, what I would suggest in this situation is to maybe like get a good orientation from the top. You can click like that T key that I was talking, the T key for going to top, and then like side for side. So yeah, so you can click the T key for top, but you can see that like when you move your mouse, your right right mouse button, when you like move from side to side, you can see like it's kind of gives a perspective view. We can change this to parallel, so everything looks parallel when you're looking down on the CAD geometry. The way you do that is just go to like this camera icon up here, projection mode, and then change perspective to parallel. So now we can adjust a little bit more accurately. So like that, we want to get like a decent fit on there. And then we're going to be rotating it afterwards to properly get the correct angle. So what I would suggest is try to get this corner lined up here, and then we can make that as a rotation axis and rotate around that line, so that rotate around that axis so that this like outside part of the duct can match up with the outside part of the radiator over here. And then don't forget about the heights, matching up the height of the duct. So again, just use your S key to get a side view, and just click it again if you want to like flip between the two sides. And then just, again, use that arrow to sort of like just drag it into place. It doesn't really have to be perfectly precise, honestly. Like, that looks really good to me. Let's see at the bottom. Yeah, that looks good. Okay, yeah. Let me just check the top again. Can just move that a little bit more so that it like intersects a little bit. Okay, yeah, I think that's good. Okay, so, and then you can just click OK. And now we have this so far in our CAD geometry. It's not perfect, but closer. So again, we want to just transform this, but instead now we want to just use a rotation. So go to transform and then rotate. And basically at this point, we would want to use a specific coordinate system so that we can rotate about that specific axis. So the way that we do that, we can click cancel real quick, and then go back to our simulation tab up here. And then to create a coordinate system, it'll be under tools. And then you can open up the node next to coordinate systems, open up the node next to laboratory, and then you can right click local coordinate systems, go to new, and then Cartesian, since we want to create a new Cartesian local coordinate system. And what we can do now is define the axes of that coordinate system. And it would be really difficult to like actually get the specific XYZ origin, and then also like the specific direction of the axes. So instead, STAR has this kind of helpful feature. You can just click on that bottom bottom left, and which allows us to basically select 3 points, which specify 2 axes, and then the third axis will just be the cross product of the 2. So basically, what we want to do here is specifically select the origin, and then we'll select like points on the x-axis and then a point on the y-axis. So to get a better view, I'm going to hide the radiator for a second, since it's a little bit difficult to see. Okay, yeah, that's a bit better. And then you can click like this top thing here to like show the mesh, and it'll just like basically show the parasolid geometry lines. Also, this black color makes it really difficult to see lines on it, so we can change that real quick. The way to do that, go to 3D CAD, duct, and then change the color here. Let's say gray. I think that should be good. Yeah, that's a lot better. Okay, so back to the coordinate system. So right click the local coordinate system, Cartesian, click that left bottom thing right here where we can select 3 points. And from there, essentially, we just want to select the origin. We'll say that this is our origin point. So you just click right here. And then we want to follow in the x-axis. So basically just follow that that line that's showing up, and then try to align it as best as you can. So that's our x-axis, and then just click once you got that. And then now we can define our y-axis, and now we have our coordinate system right there. That little blue thing, blue whatever, like datum coordinate system. Okay, so now that we have that, we can, and it looks good. It looks like the axes are aligned properly. We can just click create, and that will create our coordinate system. So now we have this coordinate system, and we can rotate the duct about this axis. So the way to do that is go back to the 3D CAD tab at the top. We want to right click duct again, go to the same transform tab, except now we'll be using the rotate instead of translate. And under axis of rotation, axis type, under coordinate system source, we'll be changing that to imported. And then where it says laboratory, we'll be changing that to Cartesian 1. Speaking of which, we should have probably renamed that local coordinate system to like maybe duct behind or something like that, so that if we have like multiple coordinate systems, we can we know which one's which. That's okay for now since we're only really having one coordinate system. So yeah, so it just defaults to 90 degrees, but we can just change that. So let's just check what 5 degrees looks like. That's in the wrong direction. Let's see, -5. Oh, sorry. -5. -5 looks, actually doesn't look that bad. Okay, actually probably -4 point something is what I would guess. Yeah, I think that's good. Basically just want to like have about the same like intersection amount on this side as on that side, then we know like it's aligned. Yeah, so that looks good. That looks good to me. Yeah, it looks good to me. Yep. So then just click OK. There we go. Just moved into place. Another thing, it looked like when we rotated it, it got offset a bit. That's not a big deal, but it's kind of bothering me. So we can just fix that real quick. So the way to do that, you can just edit the existing move body feature. So you can just right click move body one, click edit, and then just move the Y down a bit. I think that would be good. Yeah, looks like that's good. It's aligned pretty well. Yep. Okay. That looks good to me. Okay, so let's take that off. Okay, so yeah. So we have our geometry set up. Another thing to note is that occasionally there will be, yeah, let me just review this one part a bit. After, okay, the rotate part, yeah. So the way that we would do that, you want to wait. So where did you get stuck, Molly? Do you want like
I have my coordinate system now, but then when I
okay.
click like 3D CAD, it goes away.
Okay. Yeah, we don't need to see the coordinate system when
Oh.
in the 3D CAD, since like it's part of like the imported coordinate systems, and we can just select it. Wait, so like when you right click duct and then you go to transform and then rotate, rotate.
Like rotate is grayed out for me.
Rotate is,
Like I can't click it. Like do I have to leave some mode?
Do you still have like that edit on the right of 3D CAD? At the top?
Why
Like,
don't
do
you
have an
share your
edit
screen?
tab next to 3D CAD?
You want me to share my screen?
Yeah,
It's disabled.
it should be enabled now.
Okay. Okay.
Yeah, in there, just oh,
So like when I right click.
in that you have
Wait,
to
wait,
go
yeah.
in that edit tab and close it.
Yeah, what Anna said. You just have to say,
But see, it looks weird.
wait, just click return. What? Wait, oh yeah, just yeah, go back to the edit, and then go back to edit, and then close at the bottom there, and then try that again.
Okay.
You
Where am
and then oh, sorry, right, yeah, imported, and then yeah, that's it. And then just change the angle right there.
What am I changing it to?
I think it was negative 4.5. Oh. Yeah.
Yay. Okay. I think that was it then. Thank you.
For sure. Okay, let me reshare. Okay. Cool. So now everyone should have this like geometry here. We can see our baffle, or I don't even really know what to call this, whatever this middle plate thing. Now that we have that there, we can start moving on to the other steps. We want to now, since we have, before that, sometimes when we import our 3D CAD, there will be like issues with it. For example, there might be holes which need to be covered up, and so forth. And then the way to fix that basically would be to go to repair geometries. Yeah, because it's kind of difficult to show you without having an issue here. So I guess we'll just move on. Okay, so we have our 3D CAD. That's all good. We can close our 3D CAD now, or we'll update and then close. And let's just clean up some of these nodes here. Also, in case your star crashes, you should probably save our file. Yeah. All right, so now we have our 3D CAD model 1. We can create a geometry part from that. So the way to do that is to right-click 3D CAD model 1, and then click new geometry part, and then just leave all of these settings as is. Click OK. Now we have our like CFD geometry. Previous one was like a CAD geometry. Now we like have our like CFD geometry. And then again, like in the last tutorial, the way that we can view it is create a new scene. So you can right-click scenes, new scene, and then geometry. And then everything, we should see our CFD geometry in here. Okay, so everything looks good. The only thing that I'm going to change is I'm going to remove the second and third elements from the wing, simply because I want to analyze effects specifically from changing the geometry of the duct. So that just pretty much just makes things a little bit more difficult. Since there are like added variables in that, we just want to first like optimize our duct as much as possible, and then we can add these in later and just verify that that is the correct optimized model that we have. So we can remove that from our parts simply by just going through these and and finding which one it is. It looks like it's body 2. We can delete that. Are you sure? Yes. And then delete body 4. And the reason I'm only deleting the ones from the left side of the car is because, as you'll see in a second, we only really need to model half the car because the car is symmetric. So we could just multiply the forces on our airfoils, forces on the body of the car just by 2, and we get our expected value for downforce or whatever it may be. But in the case of the radiator mass flow, nothing really changes. So that's even simpler. We don't even have to multiply anything by 2. We can just measure the mass flow directly. Okay, so now what we can do is create another part, and this part is going to be our simulated wind tunnel, essentially. So we're just gonna like basically put this car inside of that wind tunnel. So the way to do that is to right-click parts, put a new shape part, block, and then we want to create our wind tunnel.
Wait, where was
that? Sorry, right-click parts, and then new shape part, and then block. Nice. Okay. So, and then now we can basically create our wind tunnel with the dimensions that we want. So, there's a general rule of thumb for the size of the wind tunnel. Let me pull up the specific dimensions. It'll take a second. Okay, so basically the standard is we want 5 times the length of the FCA car in front of the body, 10 times the length of the car behind, and then the height of the tunnel should be 2.5 times the length. So basically what we can do is just get our measuring tool real quick. Where is, oh, here, measure distance. And basically we can just go from a top view and then just get like an approximate for how much that is. Why? Okay, so that's not good. I'm trying to measure from the nose cone. To the rear here. Okay, that's not bad. Okay, yeah, that looks good to me. So it's about 2.5 meters, let's say, is the length of our car. So let's now create that block. Okay, so we should note down what these initial values are for the x direction. So it looks like it's 0.9 meters right now. We want to add 2.5 meters times 5. So what is that? So we want to add 12.5. meters to this value. So 12.5 plus 0.9 is, so 13.4 should be that. And then the rear is 10 times the length. So we want to change that x distance. So our initial is negative 1.75. So we want to add 2.5 times, oh, sorry, not 2. Yeah, 2.5 times 10. So 25 meters behind the wind tunnel. So 25, that becomes negative 26.75. Negative 26.75 there. And for the z direction, so that's what it is, okay. Let's change that baseline value from 1 meter to 1.09 meters to 2.5 times 2.5 is 6.25. So 6.25 meters up would be 6.25 meters actually total height. So what we could do right here, do some quick maths and we can find out, okay, so it looks like the total height right now is 1.1 meters. So basically just change that height to be, oh yeah, I guess this could just change to 6.5, 6.25, sorry, that's it. One other thing to note is that the bottom part of a wind tunnel needs to intersect slightly with our wheels. The reason for this is that we're going to simulate the wheels to be a rotating medium. So essentially, yeah, we want the wind tunnel to be intersected a little bit so that there's no complications in the CFD calculation. So the way to do that is we can just change the z value till we think it's appropriate. Let's see, 0.01, what does that look like? That might be a bit much. Oh, shoot. Did that just, oh my God, great. Now we have to do that whole thing again. Do you guys have what are the numbers for these? Can somebody let me know?
I think it's negative 26.749.
Okay, negative 26.
Your next one was 13.9 with a bunch of nines.
Okay.
And then negative 0.70485.
Negative point, what was it?
70485.
Wait, negative 7 point?
0.7.
Oh, 0.7, okay. 0.7.
485.
485, okay.
And then the next one's the same thing, but positive.
Okay.
And then 0.
Oh, right, yeah, this is the one that we were trying to change.
And then 6.25.
Okay. Thanks. Okay, so yeah, so why don't we make this the height, instead of 0 on the z direction, make it 0.005. And then one last thing, we need to change our y direction as well. So we could just change that to be the same as total height. So basically, we can do is just make 6.25 minus 0. It's about 5.55. Okay. So let me just see which corner it is. Okay, so yeah, this one. 5.55. Okay. Now we have our wind tunnel. Nice. Another thing to note is you might be wondering why the length on the rear of the car is more than the length on the front of the car. And reason for that is wake disturbances are usually a bit complicated. So we want to have a little bit more space behind the car for the air to normalize out before it gets to the outlet. Versus there in front of the car should be free stream, should be pretty uniform throughout, except when it gets closer to the car. So that's the reason why the rear is significantly longer than the front. Yeah, so this will be our simulated wind tunnel. We can click create, and then it's finished. We can click close. Now we have our block. This geometry scene isn't showing it right now. Whenever that happens, you can just go to scene plot up top when we have the geometry scene open, and then we can just select the parts that we want to view just by clicking over here, clicking on the parts like blue folder, and then clicking on the 3 dots down here next to the properties, and then just select the block so that we can view everything there. Yeah. Yep. And then just click OK. There's our outline that shows up. Now we can open the surface node and then do the same thing there. Then just click on that, and now it shows. Nice. Another thing that we could have done is literally just drag this block over here and then just click outline 1, surface 1. They're now checked since they're since those are existing displayers that are there. So yeah, so now we have that there. And that is our car. One other thing is that since we are only going to be modeling half of the car, that block needs to be edited so that the right side of the car right here is at the 0 point halfway. So we could just change this negative 0.7 value to just 0, and it should be exactly halfway. And just click apply, close, and then there we go. So yeah, so this is what will be modeled. Nice. Now what we want to do is, since this is going to be like our simulated wind tunnel, we want to basically specify what are going to be the inlets, the outlet, and whatever. So what we can do now is right-click this block surface and split by patch. And now we can just name the sides correspondingly. So this will be the inlet. Click create. This will be the outlet. Click create. And also, we want to denote this to be our main symmetry plane. So we can denote that here, symmetry create, and also we want to denote our ground, since we will be making changes specifically to the ground in terms of boundary conditions. Now that those have been created, we can click close, and we can now see that these surfaces have been split up into the sides that we want, outlet, the symmetry plane, our ground, and then just the other walls. We can rename that to just walls. Nice. So now what we want to do is complete a subtract between the car and the block, so that we can basically specify our entire volume of air that's going to be existing. But before that, we want to unite all of the parts of the car. So the way to do that is pretty simple. Basically, go to Operations, right-click, New, Boolean, Unite. And the reason why we're doing this is because, I mean, you might ask that because we already have like a body group 1, which corresponds to the entire like car. But once we unite the geometries, then the subtract becomes a little bit more coherent. So we basically just want to select all of the bodies in under body group 1. You could just click it once, and then just click OK. We can execute that. And now we have our unite, which is all of the parts united together. All right, so now we can do our subtract Boolean to get all of the fluid specified by the CFD software. So the way to do that, same thing, go under Operations, New, Boolean, and instead of unite, subtract. And now the input parts are essentially going to be the unite and the block, our wind tunnel. The target part is going to be our wind tunnel. All the air is going to be inside of the wind tunnel, but exterior to the unite. You can just click this execute operation upon creation so that we don't have to execute that again. And now we have our subtract, which is the subtract is just all of our air, essentially. Nice. So now what we can do is let me think if I'm forgetting anything. I do not think so. I think we are good. Yeah. Yeah, we're good. Okay, cool. So now what we can do is we can assign our parts to regions, so that we can set up proper boundary conditions, set up like the velocity at the inlet, set up the outlet conditions, set up the ground, whatever conditions we want to do with that, set up the symmetry plane, etc. So the way that we do that is we go to subtract, which is currently a part, right click, and assign parts to regions. So one key part here to note is that not only do we want a region for our subtract, which is going to be all of our air, we also want a porous region for our radiator, so that air can essentially flow through the radiator, and we can measure the mass flow rate through the radiator. So the way that we want to do that is under this menu here, we can find our specific radiator, which is actually, it's body 27. STAR basically just automatically names these files based on the parasolid that's imported, since those names don't carry over once you make a parasolid file from an assembly. So sometimes it can be a little bit weird with the naming scheme. And if you wanted, you could actually just go through all of these in the parts and rename them to the corresponding parts on the car. But I just remember that the radiator should be body 27. Hopefully I'm not wrong. And then what we want to do is create a region for each part. What this does is it creates a region for the subtract, which is going to be all of our air, and another region for our radiator. And then we want to create a boundary for each part surface. Remember, we created different part surfaces like the inlet, the outlet. So now it's going to create a boundary for each of those part surfaces, as well as a boundary for each of like the car's surfaces. Or we can leave these two as is, and then just click apply. And now we have our regions. So let me just, okay, so yeah, that was the radiator, nice. So now we have these two regions. You can see that this is right now a fluid region. The radiator is not a fluid region, it is a porous region. So we would change that to a porous region right there. Also, let's rename that to the radiator. Nice. So this is good. Now what we want to do is set up our boundary conditions, which, okay, nice. So yeah, so the ground is going to be a wall. The inlet is going to be, the type is going to be a velocity inlet, since what we're going to do is essentially specify the velocity at which air is coming in at all the locations in the inlet. The outlet is going to be a pressure outlet. Symmetry plane is going to be a symmetry plane. So are these other walls, since they should be symmetric about to the other side as well. Okay. The ground, no, because we're going to change something with the boundary conditions a little bit later. Okay, so now from here, we can set up our physics conditions and set up our mesh. And then a couple more things, and we can run. Okay. So that we can see our model, let's hide some of these walls. So hide, and then hide. Okay. So let's set up our physics continua, and then we can do some of the other steps. So the way to do that is right-click continua, go to new, physics continuum, and now we can select the models for our physics continuum. So three-dimensional flow, that should be pretty self-explanatory, I think. Gas, again, pretty self-explanatory. Coupled versus segregated flow, I talked about this last time. We have flow going underneath Mach 5, so segregated flow works a little bit better. Velocity we're going to be inputting here is 15.64 meters per second, which is 35 miles per hour, which is the average speed of our car. And 15.64, that's much lower than 100 meters per second, which is the point at which we'd want to choose ideal gas, since air becomes compressible at that point, and the density is no longer constant. So we can just choose constant density. We're using a steady flow simulation, turbulent model, and K omega, which is good for external flow situations. And that is it. Okay, nice. So we have our physics models set up. One other thing to note is that let's set up our initial conditions for our physics. I talked about this a little bit last time, but we're actually going to be using it this time. We will set up basically the initial velocity of all of the fluid in our entire region to move at negative 15.64 meters per second in the x direction. So you can see, yeah, like the x direction is pointing out this way, so we want fluid to go in this way. So negative 15.64 meters per second. And what this does essentially, like I said before, it makes all the fluid in the region go at 15.64 meters per second at the start. And this just makes it easier so that basically the flow doesn't have to just start at the inlet and then propagate all of its calculations between the individual cells all the way to the outlet. It just makes things a little bit faster so that we can get to our solution quicker. Okay, so our initial conditions are set up. Now, let's set up our wheels as a rotating medium. And then I think from there, we can do our mesh. Yeah, okay. Yeah, I think so. All right. So the way that we set up our wheels as rotating mediums is that we first want to create coordinate systems for our wheels. So it's very similar to what we did before, except now instead of using 3 points to define those two axes, x and y, we use 3 points to define a circle. 3 points on a circle to define the axes. So again, open up the nodes next to tools, and then let's create a coordinate system. Here's at this point, we probably want to rename this to duct. And now let's create a new coordinate system, right click, Cartesian. And then we click, instead of that bottom left, we click this bottom right thing right here. And then turn on our show mesh so we can see like all of like the parasol lines and whatnot, so that we can like get better alignments. Basically, all we have to do here is select 3 points on the circle. So I'm going to select 1 point here. I'm going to select another point here. Let me zoom in a little bit so it's a bit more accurate. And I'm going to select another point here. So that becomes, oh, yeah, there, nice. So that becomes our 3 points. And you can see like it creates this coordinate system right at the center of our tire, which is awesome. That's what we want. Let's just make sure that that's properly aligned. Yeah, it looks like it. Looks like it to me. So yeah, so basically we will rotate those tires about the z-axis, specifically about the negative z-axis, because we want our tires to rotate this way, obviously, and then right-hand rule. So the z vector is pointing in there. So the negative z vector would be like this. Right-hand rule would make the rotation this way. Yep. Okay. So now we can create that coordinate system. Let's close. Let's rename that to front wheel. Let's create our rear wheel coordinate system. Same exact thing. New Cartesian. Let's click the 3 points on here. Same exact thing as before. Also, I haven't checked with you guys in some time. Am I going too fast?
I wouldn't mind you like slowing down like a tad bit, but it's not that bad.
Okay. All right, I will. Okay, so now we have those 3 points. And there's our z-axis. Is that aligned? Yep, it's aligned properly. There, cool, and it's at the center of our tire. Exactly what we want. Nice, so we'll click create, close, and then again, rename that to rear wheel. Now we have those 2 coordinate systems and we can set up those tires as rotating mediums. Okay. Nice. So now let's go back into our subtract and let's go through our boundary conditions again. Let's fix our inlet to have a specific magnitude of velocity that we want, 15.64. This is a magnitude, so we don't need it to be negative. Yep, outlet, that boundary condition is set up correctly. And now let's just find our wheels. So looks like body 23 and 24. 24 is our front wheel, so we can set this up to be a to have a local rotation rate. Let me just remember how to do that real quick. Okay, yeah, so I'm pretty sure it's here. Yep, okay. So under the physics conditions node, click on the tangential velocity specifications, and we'll specify the wheel to have a local rotation rate. And that is good for the physics conditions. Under the physics values, we can select the specific axis that we want. So we don't want the wheel to rotate about the laboratory axis. We want it to rotate about the front wheel axis that we set up. And then we want it to rotate in the negative z direction. Yeah. And then let's specify what that rotation rate is. So basically, the way to do that, if the car is moving at 35 miles an hour, we would just pretty much just find our diameter, and then what would we do? How would we do that calculation? Let me just think about that for a second. Okay, yeah, so it rotates. Okay, yeah. So one full rotation is 2 pi. So if we're saying so the diameter would be, we would have to calculate what the diameter is. Let's do that really quick here. Using the measuring tool. Sometimes the measuring tool can be a whack like that. Like clearly that's not what I wanted. But yeah, it wants you to click like on a specific body. Otherwise it doesn't really understand. Oh, shoot. Otherwise it doesn't understand where you want the measuring to occur. So let's say we want to start there and then end up about on, oh, is that it's the other tire. And then we want it to end up on, yeah, I think about there. So our diameter. So like, yeah, right there should be good. Okay, so it was off. Why does that seem so much more off from a top perspective? Oh, because it's not on the exact sides. Okay, that's annoying. Okay, well, I guess just take my word for it. It's gonna be, I think it was 76 point something radians per second. 76.97. Yep. So just change that to 76.97. And then we want to do the same for the rear wheel. Yep, so set up that to be a local rotation rate, and then set up the physics values, the axis to be our rear wheel, and then the rotation rate, oh, needs to be the negative z. And then the rotation rate is 76.97. Okay. So now we have our rotating medium set up. There and there. That is good. One last thing that we want to do is set up our our radiator. And the reason for that is when air goes through the radiator, it's not going to go straight. It's going to go at an angle. Right, like it's going to go like this instead of like just straight with the oncoming flow. You can't really see the angle as much, but you know what I'm saying, right? That's we don't want the air to be able to go just straight through the radiator since we set it up as a porous region. So we want to set up a coordinate system and specify our the direction in which the air can flow through the radiator. So the way to do that is let's create a coordinate system for the radiator. Same thing as before, Cartesian. We can use that 3-point thing that I was talking about earlier. Select this to be our origin. And then that's our x-axis. Now let's get the y-axis. Okay, nice. So there's our coordinate system right there. So then click create, close. Let's rename that to radiator. Okay, so from there, we can set up the boundary conditions for the radiator. Right here under this region, what we want to do is set up oh shoot, I forgot a key step to separate the radiator into separate the inlet and outlet of the radiator. My bad. Okay, so we're just gonna have to do that real quick. We can just delete the radiator and then open up our body 27 and then split by patch. That's our inlet. Create. That's our outlet. Create. Close. default, change that to sides. Now we have that. But now we have to execute these operations again since the geometries were slightly changed, or since the parts were modified. So to quickly do that, just right-click operations and then execute all. Sorry about that. Okay, cool. So now we have that set up as we want it to be. And let's see real quick if we have the proper. Okay, so yeah, we'll have to reassign this to regions. Okay. Wait, no. Wait a second. Yeah, that's not what we want. We'll have to just do that region thing again. Okay. So pretty much just do as we did before. Assign parts to regions, include the subtract, and include the body 27, one region for each part, boundary for each part surface, apply. And now we should have the proper setup here. Yeah, inlet, outlet, sides. Okay, cool. And then block inlet, outlet. Okay, cool. That is as we want it. Okay, sorry about that, guys. So yeah, so now let's just set up our inlet again as a velocity inlet. We want it to be 15.64. Outlet, that's good. Oh, we just need to change that to a pressure outlet. That's as we want it. Change this to a symmetry plane. Change the walls, the side walls, to a symmetry plane as well. Okay, nice. So that should be good. Another thing is for the ground, we want to specify that as a slip condition. So remember before when I was talking about the no slip condition in our last tutorial? If we think about the ground should be moving relative to the car. Since the car is stationary and air is flowing in from the inlet, there's actually two ways to set this up, really, to model that correctly. You can either set up the ground to be moving with a relative velocity at 15.64 meters per second, just as we set up the tires to have a specific rotation. But this is just simpler. You can just make this as a slip condition, and it'll basically have the same effect in the end. Okay. So let's see. That's good. Okay. So again, make sure that that's a porous region. And then let's set up our okay, so we can just set up our boundaries. So what we want to do here is basically we don't really need to change anything, even though this is a wall. This entire thing is a porous region, so air can still flow through it. What we want to specifically do, though, is connect the inlet in this region, in this radiator porous region, which is a separate region, to our boundaries of the radiator inside the subtract, so that basically they can communicate together through something called the interface. And they'll basically just communicate together through the interface, and we can get the accurate values of mass flow through the radiator. So the way to do that is to click on one of the inlets in the subtract region. It's called body 27.inlet. And then after clicking on that, control, and then click on the inlet in the radiator region. Then what we can do from there is right click and create an interface between the two. And now that interface can basically just communicate together about like just the velocity going at certain locations or whatever it needs to do with the Navier-Stokes equations and whatnot. And then same with the outlet. And we don't have to do that for the sides because there doesn't need to be any information communicated between the sides. Okay, next step from here is, like we said before, we want to specify the direction in which the air can flow through the radiator. So the way to do that is to go under physics values, and then under let me just see if I'm okay, yeah. We want to change the porous viscous resistance. So basically what this means is, I mean, just think about resistance. We want to minimize the resistance in this X direction, but increase the viscous resistance in the Y and Z direction so that airflow basically cannot move in those directions, and therefore all the flow going through this will only have an X component and basically no Y or Z components. So the way that we do that is we set up a really high value for the XX component of the porous viscous resistance. I mean, sorry, a really low value for the XX component of the porous viscous resistance, so it has a really low value. So let's just say 70. And then a super high value for the YY or Y and Z components of the porous viscous resistance. So for example, we would just set up like 10,000 on each of these. 10,000. Yep. And now we just want to specify what specific orientation we want. So what are the axes that we'll be using? And we can do that essentially by changing it here, going to Orientation Manager, and then opening up the node next to that, clicking on Local Orientation 1, and then changing that to Radiator. Okay. That should be good. Let me just think if I'm forgetting anything. No, I think we're good to mesh. Yeah. Yeah, I think we're good to mesh. Okay. Yeah. Also, another thing, we want to create a new geometry scene. Never mind. Yeah, that's good. Okay, cool. So yeah, we should be good to mesh. Okay. So the way that we mesh, same way as we did it before, under operations, right click, new, mesh, automated mesh. And we want to mesh on the subtract. And then also on that radiator. So yeah, so we'll just select the trimmed cell mesher, which is good with external flows, prism layer mesher, and then the surface remesher. We can click automatic surface repair, doesn't hurt. And the values that go here, I'm just going to list them because basically the way that we arrived at the specific values that we want in our wind tunnel sims is by just trial and error going through a sim and then seeing if we have proper convergence of our residuals, and if not, changing some parameters in our mesh, and then we arrived basically at these specific ones. So I'm just going to go through that pretty quick. So base size 0.05 meters, target surface size 100%, minimum surface size should be 10% already, surface curvature is good, surface growth rate, that's fine, number of prism layers, change that to 5, prism layer stretching 1.5, total thickness 30%, that's good. That's good. Okay, volume growth rate, fast, and then slow on surface growth rate, maximum cell size, 1 meter, post mesh opposition, nothing. Okay, cool. And then under custom controls, we can basically set up custom surface controls to specify the mesh characteristics on specific surfaces, like our airfoil, the body of our car, yeah, etc., etc. So let's look at that. So first, the chassis. Let me see which those include. So those are just all the rods essentially. Okay, so what we want to do is right click custom controls, new, and then surface control. And then we want to specify the part surfaces that we want. So it would just be under subtract, unite, and then we would find the specific chassis parts. Don't remember what are the names of the others. Okay, so boss extrude 2, 5, and 4. Looks like, no, not all of them. And then, okay. 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 So we'll just select all of the, yeah, we'll select those. Okay, cool. So under the surface control, we'll click these, I'm pretty sure. Yeah, okay, cool. So those are all our chassis parts. Then another surface control for our main plane. Let's see, another one for the domain. And another for the radiator and duct. Okay, so now we'll select the part surfaces for each of these. Under subtract, it should just be the entire block. That's our domain. For main plane, I think it was, yeah, okay. Boss extrude 2, that's our main plane, and then radiator duct. Select our part surfaces, duct and body 27. Nice. So now we want to specify our values. Let's see what those are. So we have a changed custom target surface size, a custom minimum surface size, and those values are 12.5 and 6.25. Wait, was that for the, yeah, that was, okay. So 12.5, oh, the wrong one. 12.5 and 6.25 for the domain. I think that was just 1 meter for both. Yep. Target surface size, custom. Sorry, I'm going a little bit fast, but I just want to get through this mesh thing here. And then for the main plane, now we want to probably control target surface size. We want to control the amount of prism layers there are. We want to control surface curvature. And we want to control surface growth rate. Custom values. Oh, and under prism layers, customize number of layers and thickness. Okay, cool. So we want 25% here. We want 10 and 12. 10 and 12. I talked about the prism layers a little bit on the last video. So I guess if you want to understand that a little bit more, you should refer back to that one. Minimum surface size, 3.125. Surface curvature, 80 points per circle. Since this is a pretty tight radius, we want to model that appropriately with more surface curvature. Yeah. And then surface growth rate. Let's see if that, okay, so it's changed to 1.2. Okay, cool. Nice. So main plane is done. Now just radiator and duct to do. Okay. Let's see, what are the values we need to change? Target surface size. Custom. 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 Surface curvature. Custom. Surface growth rate. Surface trimmer. Surface growth rate. Okay. Custom. Oh, forgot about the prism layers. Customize number of layers and total thickness. Also, there's a pretty simple calculation to see how thick your boundary layer should be. I won't get into that right now though. But it is basically just like, it's dependent upon your Reynolds number. Maybe I'll cover that in the next video. Okay, cool. So let's change these values. 15%. Number of prism layers, 10. Okay, so 15. 15, minimum surface size, 5, surface curvature, 75 points per circle, surface growth rate, I think is the same, and then trimmer surface growth rate is set to slow. Okay, finally, done with all of our mesh inputs. Now we can click per part meshing, since we separately selected the subtract and the radiator. And then also we can select parallel if you set it, your computer to have run on multiple cores. I'm expecting this to take a really long time. So what I'm going to do instead is I'm going to change the default control, the base size to be. You know what? Let's run it and see. But it may take a really long time on your guys' computer, depending on your processing power. Okay. Looks like we'll just take like another minute or two. Just clean up some of these nodes. But usually this like super long setup, you won't have to go through for each sim. Like if you're running like a bunch of sims for like a specific thing that you're trying to optimize, you pretty much only have to set it up once, and then like I showed before, you can just model re-import, and then you can right click your operations, execute all, clear your solution, and then run, and that's it. You'd want to save as, of course, so that you create a new simulation so you don't overwrite your old data. Okay, though, it looks like it's finished its mesh. Now let's take a look at the mesh by creating a mesh scene. Okay. Nice. So we can see that we have half the car. Nice. Let's hide some of these sides so we can see the mesh on the car itself. You can see that I've made the duct mesh a little bit finer than the rest of the car, because I mean, we are trying to optimize the duct geometry, so we want it to be as accurate as possible. But yeah, so the mesh has been set up, and there's nothing else to really do other than run. Of course, we want to look at a specific value that we're calculating. So that would be mass flow in this case. So the way that we could do that is pretty simple. Right-click reports, new report, and then we just go to mass flow, set the part that we want. And this is where the interface becomes a little handy, since it'll communicate the data of the mass flow between the radiator porous region and that just regular standard subtract fluid region. So it will communicate that data with each other, and we just need to calculate the mass flow through the inlet of that radiator. Then click OK, and our sim is ready to run. So yeah, I mean, that is pretty much it. Oh, no, that's not it. We want to take a look at what the flow is doing. So specifically through the duct. So we know what's going on. So let's create a plane to view the velocity vectors upon. The way that we do that, right click the right parts, new part section, plane, and just make that plane normal to the z-axis. Oh, sorry, just by inputting a 1 there. And then what we can do is we can set it so that it can basically sweep through our entire duct. So what we can do is we can set the plane to start at the bottom of our duct. Okay, that looks like it's good. Okay. And then just click create. Close. We have our derived part now. Can even just drag it here if we want, just to look at what the mesh looks like. I mean, looks pretty similar to what the floor looks like. That's not really that helpful. But what we can do to actually view the velocity through on that plane is create a new scene, except now it'll be a vector scene. And usually it doesn't show the surface of a vector scene immediately. So let's go to scene plot, change this instead of just outline to also surface. Click that right there. And then let's hide some of these sides. And then let's get our derived part in here from our simulation tab. And then click vector 1 since we want our vector of velocity to be plotted onto that plane. Click OK. Yeah, we can see, we can't see that plane yet, actually. If I change this to line, yeah, there it is. Okay, yeah, so now we have our plane to view the flow through the duct. We have our report, which we can make a plot and monitor and plot from, so that we can check back on this every now and then, see if the value has converged to a specific value, see if the plot has converged to a specific value. I think this is it. I think we can pretty much just click run at this point. Yeah, that should be it. Okay, so let's see. Let's click run. I hate that perspective mode. but we should just default it to parallel. Okay, but let's see. Yeah, so it just did its first iteration. Oh, let me pause it here. So this is what I meant by the initial condition being 15.64 meters per second that we set up in our physics continuum. All of the flow is moving at 15.64 meters per second, so that it doesn't have to like propagate all the way through. And then it'll slowly figure itself out as it goes on. And create our final solution of flow. But this will take a really long time to run, usually like a couple hours. So for a full car sim, so we won't like look through this, go through this. But I just want to note a couple of things. Can monitor our mass flow here, and then also if we want to look at the streamlines through the duct, that's another derived part. What we want to do first, though, is create a constrained plane. We want it to snap to the duct inlet. Okay, no, that snap from the front. Okay, that should have worked, I think. Yeah, so now it's snapped to our duct inlet. That is our plane. Now we can select our contour and just sort of just outline the duct at this point. So just click like the top. Oh shoot! Let me just clear the loop. I just wanted to angle it a bit. Okay, but yeah. So let's do that with here. So I'll click. Let me see. No, that doesn't help. I'll click that point. This point. Shoot. That point. Geez, this can be a little frustrating to work with. Okay, let's see if we can get this right. I want to click that point right there. Modify the contour. Why isn't it letting me? Okay, I'll just clear the loop. Try this again. Okay, so oh my god. 1.2 points. Oh my goodness. Oh my god. Now I have to clear the loop again. This is really frustrating. Oh my god. Okay, I got this. All right, so 1, 2, 3, 4, and then connect it back. Okay, cool. That took an annoyingly long time. Okay, so now that we have that, thanks, Molly. So now that we have that constrained plane section, we can create a streamline part. So streamline, this basically just specifies the amount of streamlines in the specific direction. So we can just leave it as is for now. It's not that big of a deal. But the seed parts, we want to select that new constrained plane. basically what this will do is it will find the streamlines in front of that plane and behind of that plane. So we can just identify exactly the flow that we want to look at. So that's where we just selected the direction both. So basically it'll integrate the velocities to find the direction that the flow takes as a function of time in behind and in front of that constraint plane section. And then let's click create, and those are our streamlines. So another thing that we can do is make it so that the color represents the velocity, since we like pretty colors. But yeah, so those are our streamlines. And since we would ideally want to see what the streamlines look like on the inside, we would just hide the duct just like that. That's it. But yeah, that should be it for now. But also, I just want to point out this one thing. Do you see how the flow directly changes direction once it gets into the radiator? That's because of that porous viscous resistance that we set up earlier. So that doesn't just go straight based on where the flow wants to go. It's specified by the radiator geometry. So I mean, at first glance, it looks like there's no flow separation at all. It pretty much follows the spline exactly. But I mean, we've only run the simulation for 5 iterations. Usually we'll want to run it for like minimum of 1,000 iterations. And we want these residuals to get a lot lower than where they are. Yeah. So that is an external flow simulation. Do you guys have any questions? No? Okay. Well, it looks like we finished right on time. Cool. That took a long time.
You're gonna put
But
this on the Slack channel, right?
you mean the recording?
Yeah.
Yeah. I'll put it in the Google Drive and I'll link it in the Slack channel.
Okay, thank God.
Yeah. It's a lot. It's a lot. But yeah. So no questions. Okay.
Thank you.
Alrighty then. I will see you guys on shop hours on Monday.
All right, thanks, man.
Thanks,
For
Rob.
sure.
Bye everyone.
Bye everyone.
See ya.